Good day, everyone, and welcome to this in-depth lecture on the nuclear equation of state in superdense matter, with our focus squarely on the remarkable interiors of neutron stars. As of December 19, 2025, this area of astrophysics and nuclear physics is experiencing an exciting surge of progress. The Neutron Star Interior Composition Explorer, or NICTA, mission aboard the International Space Station has just released updated pulse profile modeling results, providing even more precise mass and radius measurements for pivotal pulsars such as the nearby millisecond pulsar PSRJ 0437-4715 and the heavy PSRJ 0740+6620. Simultaneously, the LIGO Virgo-Cagra collaboration's ongoing fourth observing run, known as O4, has incorporated new data from potential binary neutron star events, tightening constraints on tidal deformability parameters. On the theoretical front, chiral effective field theory calculations have been extended with greater confidence to 1.5 times nuclear saturation density, incorporating explicit delta resonances and improved regulators. Over the next 15 minutes, we will carefully unpack the fundamental role of the EOS, explore theoretical modeling strategies across varying density regimes, discuss candidate exotic phases including hyperons and deconfined quark matter, review the key observational constraints with emphasis on these fresh 2025 developments, address long-standing challenges such as the hyperon puzzle, and conclude with the far-reaching implications for quantum chromodynamics in regimes far beyond terrestrial reach. To begin, neutron stars represent the densest stable objects known in the universe, formed from the collapsed cores of massive stars following core collapse supernovae. These extraordinary remnants cram between approximately 1.1 and 2.2 times the mass of our Sun into a sphere with a radius of merely 10 to 15 kilometers. This compression yields central densities that soar to 5 or even 10 times the saturation density found in ordinary atomic nuclei, a value of about 0.16 nucleons per cubic femtometer, equivalent to 2.8 times 10 to the 14th power grams per cubic centimeter. In such conditions, matter is profoundly neutron-rich, fully degenerate, and governed predominantly by the strong nuclear force operating in highly non-perturbative regimes of quantum chromodynamics, or QCD. The equation of state, often abbreviated as EOS, is the critical relation that links pressure to energy density, temperature, which is effectively near 0 Kelvin for isolated mature neutron stars, and the specific particle composition of the matter. This EOS dictates the star's global properties through the Tolman-Oppenheimer-Volkoff equations, which describe hydrostatic equilibrium under general relativity, balancing immense gravitational forces against internal pressure gradients. The concept of EOS stiffness is central here. A stiff EOS, characterized by pressure rising sharply with increasing density, permits higher maximum stable masses and larger radii for a given mass. Conversely, a soft EOS results in more compact stars, with pressure providing less resistance, leading to lower mass limits before inevitable collapse into a black hole. The latest observations, as we'll detail shortly, indicate an EOS that is moderately stiff on the whole to accommodate measured masses exceeding 2 solar masses. yet exhibits hints of softening at intermediate densities, potentially signaling phase transitions, while radii for canonical 1.4 solar mass neutron stars hover around 12 kilometers. The historical journey of EOS modeling is rich and illuminating. In 1934, Walter Baade and Fritz Zwicky first suggested neutron stars as the endpoints of stellar evolution in supernovae. 5 years later, J. Robert Oppenheimer and George Volkoff published the first theoretical structures using a simplistic ideal neutron gas EOS, predicting a maximum mass of roughly 0.7 solar masses, far below reality due to ignored interactions. The 1960s brought more realistic nucleon-nucleon potentials through Bruckner-Hartree-Fock calculations. The 1970s and 1980s introduced relativistic mean field theories with meson exchanges and the inclusion of hyperons, which dramatically softened the EOS and gave rise to the infamous hyperon puzzle. The 1990s saw variational methods with sophisticated potentials and the first serious proposals for quark hybrid stars. The turning point came in the 2010s with the development of ab initio chiral effective field theory and the groundbreaking 2017 detection of gravitational waves from the binary neutron-star merger GW 170817, which provided the first direct tidal deformability constraints. The current 2020 multi-messenger era, fusing X-ray timing from NICER, gravitational waves from LIGO and collaborators, precise pulsar masses from radio telescopes, and laboratory nuclear data, is rapidly converging on a more unified picture, while leaving room for intriguing exotics. Now, let's examine the theoretical frameworks employed across the star's density layers. The outermost region, the outer crust, at densities up to about 10 to the 11th power grams per cubic centimeter, features a Coulomb lattice of increasingly neutron-rich ion group nuclei, bathed in a degenerate electron gas to maintain charge neutrality. As density approaches the neutron drip threshold around 4 times 10 to the 11th grams per cubic centimeter, neutrons begin to leak from nuclei, forming a free neutron gas. The inner crust, spanning up to roughly the nuclear saturation density at 10 to the 14th grams per cubic centimeter, hosts highly neutron-rich nuclei immersed in dripped neutrons and electrons. Here, the competition between nuclear surface energy and Coulomb repulsion leads to geometrically frustrated configurations collectively termed nuclear pasta. These include spherical nuclei, rods, spaghetti, slabs, lasagna, tubes, bubbles, or even more complex antipasta phases. Modern calculations use quantum molecular dynamics simulations or energy density functionals in the Thomas Fermi approximation to map this phase diagram. Nuclear pasta is believed to play a role in pulsar glitches by pinning superfluid vortices and may limit crustal strength against gravitational wave-driven mountains or R-mode instabilities. Moving to densities around and just above nuclear saturation, the outer core, chiral effective field theory emerges as the most reliable tool. Anchored in the approximate chiral symmetry of QCD with light up and down quarks, HEAFT systematically expands interactions in powers of low momenta over the chiral breakdown scale. It includes 2 nucleon forces up to next to leading order, 3 nucleon forces to next to leading order, and emerging higher body terms. Low-energy constants are rigorously fitted to nucleon-nucleon scattering phase shifts and properties of light nuclei like deuterium and helium-3. The December 2025 refinements have incorporated explicit delta isobar degrees of freedom as active particles and employed local coordinate space regulators to reduce cutoff artifacts, allowing uncertainty quantified predictions to extend confidently to about 1.5 times saturation density. These yield moderate stiffness in neutron matter. In good agreement with neutron skin thickness, constraints from the PREX-2 and CREX experiments at Jefferson Laboratory, which measure the symmetry energy slope through parity-violating electron scattering. Deeper still, in the inner core beyond roughly twice saturation density, the strongly non-perturbative nature of QCD necessitates phenomenological approaches. Relativistic mean field theories model effective in-medium interactions via exchanges of scalar sigma mesons for attraction, vector omega mesons for repulsion, and arrow mesons for isospin asymmetry, often with density-dependent coupling strengths calibrated to nuclear saturation properties, finite nuclei binding, and flow data from heavy ion collisions. Complementary non-relativistic models like Skyame or Goni interactions parameterize density-dependent effective forces. A significant complication arises when strangeness degrees of freedom become favorable. Hyperons, such as the neutral lambda, charged sigma, or cascade particles, populate Fermi seas via weak equilibration. This adds new fermionic species, opening additional channels for pressure support, but ultimately softening the EOS by reducing the Fermi pressure from nucleons alone. The resulting hyperon puzzle has persisted for decades. Basic implementations predict maximum neutron star masses below 1.8 solar masses, starkly conflicting with radio observations of pulsars at 2.01 to 2.08 solar masses and above. Current resolutions invoke enhanced repulsive interactions through additional vector mesons coupling to hyperons. Universal three-body forces involving strange baryons, or excluded volume treatments that effectively stiffen matter at high compression. At the extreme central densities of the most massive neutron stars, reaching 5 to 10 times saturation, perturbative QCD calculations for three-flavor asymmetric quark matter gain validity. These employ hard dense loop resumations, or next to leading order thermodynamics, predicting a stiff EOS where the speed of sound squared approaches or exceeds the causal conformal limit of 1/3 due to non-perturbative gluon exchanges and strange quark contributions. Constructing hybrid EOS involves connecting hadronic and quark descriptions. First-order phase transitions, enforced by Maxwell construction with equal pressures and chemical potentials, can produce distinctive mass twin stars. Two stable branches with the same gravitational mass but different baryonic compositions and radii, one purely hadronic, the other with a quark core. Smoother crossovers via Gibbs construction allow continuous hybrid stars without instability. Additional stiffening comes from color superconducting phases, such as the color-flavor locked state pairing all three flavors or two-flavor pairing in less symmetric matter, which gap quarks against weak decays and suppress direct Urca neutrino cooling, leading to observable differences in thermal evolution. Contemporary unified EOS efforts in 2025, exemplified by projects like the Munich Unified EOS Suite or the Bayesian analysis of neutron star data initiatives, seamlessly integrate chiral EFT constraints at low density, flexible phenomenological parametrizations at intermediate densities, often using speed of sound segments or piecewise polytropes to explore uncertainties, and perturbative QCD matching at high density. The speed of sound profile serves as a powerful, model-independent diagnostic. Temporary dips below the conformal value of 1/3 signal softening from phase transitions, while sustained values above indicate strong repulsion or deconfinement effects. Envision the neutron star's internal architecture as a multi-layered cosmic onion. The thin, solid outer crust of normal nuclei transitions to the exotic pasta phases in the inner crust, then to the superfluid, neutron-dominated outer core with nucleons, electrons, and muons maintaining neutrality. The enigmatic inner core may host hyperons or liberated quarks, with phase interfaces potentially behaving like geological faults, capable of releasing stored strain in starquakes, manifesting as observed pulsar glitches or even gamma-ray bursts in extreme cases. Shifting to observational constraints, multi-messenger astronomy has transformed the EOS landscape. Precise Shapiro delay and orbital timing from radio pulsars have established masses exceeding 2 solar masses, with standout examples like PSR-J 0740 plus 6620 at 2.08 plus or minus 0.07 solar masses and PSR-J 0348 plus 0432 at 2.01 solar masses. These demand the EOS remain sufficiently stiff at high compression to prevent immediate black hole formation. NICER achieves simultaneous mass and radius determination by fitting relativistic pulse profiles of thermonuclear X-ray bursts or persistent hotspots on rotating surfaces. The instrument's soft X-ray timing precision captures light bending and frame dragging effects. The December 2025 data releases include improved modeling for PSR-J 0437-4715, a 1.4 solar mass millisecond pulsar with minimal background contamination due to proximity, and PSR-J 0740 plus 6620, yielding consistent radii of approximately 12.0 plus or minus 0.8 kilometers across the mass range. These results favor moderate softening around twice saturation density, aligning beautifully with chiral EFT predictions, while leaving room for subsequent stiffening to support heavier objects. Gravitational waves from binary neutron star in spirals encode tidal deformability in the waveform phase. The dimensionless Love number L quantifying polarizability, scaling as radius/mass to the power of 5. The landmark GW170817 event constrained lambda for 1.4 solar mass stars to below roughly 800. Subsequent analyses and O4 run accumulations, including potential new mergers, have further narrowed this, disfavoring both ultra-stiff EOS, large radii, and ultra-soft ones, prompt collapse. Bayesian combinations of NICER radii and gravitational wave EOS bands, excluding broad classes of models. Supporting evidence comes from diverse channels. Thermal cooling trajectories observed in X-ray luminosities of isolated pulsars test neutrino emissivity. Enhanced direct Urca processes in hyperonic or quark matter would accelerate cooling, distinguishable from standard modified Urca in nucleonic stars. Sudden spin-up glitches in rotation provide insights into crustal superfluid vortex dynamics and pinning strength in pasta layers. Anticipated moment of inertia measurements from relativistic spin-orbit coupling in double pulsar systems will add independent leverage. Laboratory constraints from heavy ion collisions at facilities preparing for operation, like FAIR in Germany or NICA in Russia, inform the symmetry energy and its density dependence critical for neutron-rich conditions. Despite these advances, significant challenges endure. Achieving consistency between observed smaller radii at typical masses and the stiff support required for heavy pulsars frequently demands carefully tuned phase transitions, such as those producing mass twin configurations where a strong first-order hadronic to quark transition creates a third family of stable compact objects. Hyperon repulsion mechanisms must be calibrated delicately to avoid contradicting limited hypernuclear spectroscopy data from accelerators like J-Park. Nicer inferences rely on assumptions about hotspot shapes, atmospheric compositions, whether hydrogen, helium or heavier elements, and potential magnetic field distortions. Gravitational wave parameter estimation carries uncertainties from waveform approximants, particularly for eccentric orbits, high spins, or matter effects in the late spiral. Higher-order many-body forces in chiral EFT are actively being computed, but contribute lingering uncertainties at the transition to phenomenological regimes. The horizon is bright with promise. Upcoming LIGO sensitivity upgrades and the O5 observing run are projected to detect dozens of binary neutron star mergers, vastly improving statistics on deformability and equation of state parameters. Third-generation ground-based detectors, including the Einstein telescope in Europe and Cosmic Explorer in the United States, will deliver sub-percent precision on masses and radii from gravitational waves alone. Next-generation X-ray timing missions, such as the proposed Enhanced X-ray Timing and Polarimetry Mission, or Spectroscopic Time-Resolving Observatory for Broadband Energy X-rays, will push radius measurements to even greater accuracy. The Square Kilometer Array radio telescope array will discover and time thousands of new pulsars, probing extreme masses and spins. Integrated multi-messenger campaigns, coupled with machine learning-driven Bayesian inference pipelines and comprehensive EOS databases, will enable near real-time constraints as events are detected. In conclusion, as of December 19, 2025, our understanding of the nuclear equation of state in superdense neutron star matter has reached an impressive level of maturity. Chiral effective field theory solidly anchors the low-density regime, the latest Knightsia radius determinations, and LIGO O4 tidal deformability limits tightly bracket the intermediate to high densities, collectively favoring a predominantly nucleonic composition as the baseline while preserving viable parameter space for exotic phases like hyperons or deconfined quarks. This synthesis not only resolves classic puzzles, but profoundly illuminates the behavior of quantum chromodynamics at baryon chemical potentials and densities utterly inaccessible to particle accelerators on Earth, forging a vital bridge between nuclear physics astrophysics and fundamental particle theory. The decade ahead holds tremendous potential for definitive tests of phase transitions or direct evidence of deconfinement, promising to rewrite our knowledge of matter under the most extreme conditions in the observable universe. Thank you very much for joining me on this extensive exploration of one of astrophysics' most captivating frontiers. If this lecture has piqued your interest, please like, subscribe to the channel for the rest of the series on obscure space science topics, and share your perspectives in the comments below. Do you think the cores of the heaviest neutrons contain quark matter, or will future data favor purely hadronic compositions? Until next time, clear skies and continue gazing upward at the wonders of the cosmos.